Good afternoon, everyone. I'm Yihan from Fudan University. I'm pleased to share our research vision identifying affected library versions for open source software vulnerabilities. This is a joint work with Kaifeng, Bihuan, and Xin. Open source software plays a crucial role in software development. According to Simpson's supply chain security report, open source software vulnerability has a substantial impact in supply chain security. Employing software composition analysis techniques is an effective way to mitigate such security risks. The common pipeline of SCA involves parsing and extracting dependent libraries from a target project. Then it queries vulnerability databases to identify whether any vulnerabilities exist for these dependent libraries of specific version. However, if the vulnerabilities affected library versions are inaccurate or incomplete, downstream tasks such as vulnerability propagation and exploitation may be impacted, causing false positives or false negatives. Essentially, the quality of vulnerability database directly affects the effectiveness of SAA. Therefore, ensuring quality of vulnerability databases is of paramount importance. We first use one vulnerability to demonstrate the quality issue of current databases or approaches. There are 5 databases and 5 related approaches. However, there are only GitHub and GitLab adversaries that reported the true affected version. Other databases and approaches either record the wrong version or not detected any vulnerable versions, raising the quality issue are prevalent. We use another CVE to demonstrate the quality issue. The vulnerability root cause is when using bcrypt class with maximum work vector 31 for log runs. The encoder does not perform any sort runs due to an integer overflow error which occurs in line 10 in the pre-patch method. VSCZ is one of the SOTA approach to tracing the delete line within patch to the inducing commit of the vulnerability. There are 2 main limitations of VSZZ. First, in this case, VSZZ regard each delete lines as equal and wrongly tracing the line 22, 23, 28, and 29, which is vulnerability unrelated, caused 91 false positive versions in this case. Another limitation is that it cannot deal with the patch only with add lines because it depends on git blame to trace the delete line and overlooks the fixed features, which can cause false negatives. Another approach is for Java, which also causes the false positives in this case. This is the function call of the functions in the patch. It first checks the password in checkpw function, and during checking the password, it invokes hashpw and crypt raw to perform the central password hashing step in the bcrypt class. Where Java not matched the vulnerable crypt raw in this version, which is appropriate because the fixed long runs is quite different from int runs in line 6. However, it is also reported by Java as a vulnerable version because the uncritical checkpw before change in this version is detected, which causes 84 false positive versions. There is another clone-based approach, MVP. It first slicing the changed statement to extract the vulnerability related and the fixed related context. In this case, the line 22, 23, 28, and 29 is vulnerability unrelated statements, and the slicing further introducing more vulnerability unrelated lines of line 24, 30, 31, 32, and 33, which cause 136 vulnerable version matched as well. Body and reading finder is two clone-based approaches. They regard the method level match. In other words, they not consider the changed method to identify whether the version is vulnerable or fixed, which caused 136 vulnerable versions missed because of the cross signature. So, let's summarize the current patch-based and clone-based limitation. First, they consider all change methods equally important. Besides, they either consider the changed statements equally or miss the importance of statements with function level matching. These all cause false positives and false negatives. So, to distinguish the importance of vulnerable methods and patched statements, Vision performs critical method selection and critical statement selection to prioritize important changes and their context. Furthermore, the vulnerability signature is represented by weighted interprocedure program dependency graphs that incorporate critical methods and statements. As for critical method selection, we use HIT algorithm originally developed for rating web pages. In the context of vulnerabilities, authority methods are those that the synthesizer would eventually reach, while hub methods are the triggers that are likely to traverse. Additionally, intermediate methods lying between authority and hub methods are considered during the scoring iterations. Take the same CVE as an example. There are a quatrain of hash PW to crypto. We first construct the core graph, then add the additional knowledge about the method and class of the vulnerability from GitHub. If any class or method is mentioned, like crypto in this case, Vision phantom method caller for it. Eventually, the method relation graph is constructed and the critical method is determined by hits. Next, Vision identifies the critical statements. Taking the same CVE as an example, it first sizing the change statement to extract the vulnerability related and fix the related context. Then, Vision identifies the critical variable, which is for check introduced in line 1 using HunkDiff, while other variables are uncritical. After that, Vision using tint analysis backward and forward to trace the tint path of for check to get the critical statements. Next, Vision constructs the IPDG. It leverages Unix coder to vectorize the node and edge in the IPDG, and weighted the critical methods identified before as WS, while the edges weight is the average of its source and the destination. After that, the vulnerability signature IPDG pre and the patch signature IPDG post is constructed. Then Vision maps the critical functions and critical statements to the target repo and run the same pipeline mentioned before to construct the potential vulnerability signature and the potential patch signature. Finally, it uses graph edit distance to calculate the similarity of IPDG. If the vulnerability similarity is greater than the patch similarity of signature, while the similarity of vulnerability signature is greater than 0.6, the target version is vulnerable. Otherwise, it is the safe version. To evaluate Vision, we construct a large scale of databases with a high coverage and accuracy. It contains 12,073 library versions corresponding to 102 CVEs across 36 distinct CWE types within 79 libraries. We evaluated the tools against both patch-based approach and clone-based approach on GitHub repositories and on Maven. In terms of effectiveness evaluation, we outperformed the SOTAs on both GitHub repositories and Maven. We conducted an in-depth analysis of false positives and false negatives of the vision and summarized the following courses. First, the CVE or commit descriptions may contain irrelevant methods, which can mislead our critical method selection. Second, Vision leverages program slicing based on Rome, which contains incorrect data or control dependencies that can mislead our critical statement selection. Third, the library versions can have different fixing logics because they evolve on different branches, which may not be reflected in patch potential signatures. After that, we have done an ablation evaluation, which shows that removing any component of vision results in noticeable drops in precision and recall. Critical statements has the highest contribution to recall, underscoring its performance, while correlations have the highest contribution to precision, highlighting its importance. Besides, Vision have reported a lot of incorrectly labeled vulnerabilities to NVD, Vercode, GitHub, GitLab, and Snyk, respectively, and received many thanks letters from GitHub, GitLab, and NVD, while others are in progress. That's all my presentation. Thank you.